Mm,
Hello. Okay. Okay, that's fine.
Okay. Share screen. Okay. Okay, so now that I know my screen is set up, we can start. So this is the second topic that I'm teaching. Hopefully, I will round up today. Chemical thermodynamics. So even though we have talked about thermochemistry, we can still group it under chemical thermodynamics. And we talked about the first law. On the same site, I have uploaded this slide for you. So in case you want to just download it now and follow along or print it right away, but I've shared the slides here. Okay, sorry about that. I just needed to be sure that was the right slide. So that's why I went to confirm. Okay, so this is our outline for this talk, lecture this morning. Okay, so let's start. We already talked about the first law of thermodynamics. TD stands for thermodynamics. And the summary of it is that energy cannot be created or destroyed. And we looked at different relationships between the internal energy and delta H, the internal enthalpy. So the long and short that is the energy of the universe, which is the system plus the surrounding, is conserved or is constant. However, this energy can be converted from one form to another. You can change it from potential to, so we saw that from the internal energy, the potential energy in bonds can be used to do some other kinds of work. However, what has been noticed is that nature has a preferred direction. There is no way that you put hot water and it will not cool down. It will not go to a higher temperature. It cools down unless you're putting it on fire. Then so objects fall. We are familiar with gravity. So nature has a preferred direction. It doesn't always go the direction that we want it. So that direction, we call it the spontaneous direction. And the process that occurs during the spontaneous direction is called the spontaneous process. So other than being able to talk about conservation of energy, Thermodynamics can also help predict the preferred direction of a process. Once you know the preferred direction of a process, you are better equipped to know how to go about modifying that process. It does not talk about how fast the process will be. Neither does it tell you about how far it's going to proceed. It just tells you the direction, the preferred direction in which you would go. So what is a spontaneous process? A spontaneous process is a process that occurs without any external aid. Once it starts, it continues. It doesn't need any external aid for it to continue. For example, you put this, there's a gas in here, and then you open this tap, it just continues to flow in that direction until equilibrium is achieved. And once equilibrium is achieved, there's a balance. So there's nothing to force it to happen. The reverse process does not happen. That's the one that we call the non-spontaneous. When you put, so this one is a fast reaction. When you put iron in water, it rusts. So that's an example. Those are examples of spontaneous process. Like I said, it does not indicate how fast. For example, the conversion of diamond to graphite takes years, but it does happen. That is the preferred direction. Graphite does not prefer to go. So graphite and diamond, they are two different allotropes, or that is different forms of carbon. So the preferred direction is diamond going to graphite, which means graphite is thermodynamically more stable. So the speed depends on other experimental conditions. Catalysts can speed up reactions, but they cannot make a non-spontaneous process spontaneous. And a non-spontaneous process, a non-spontaneous process is the one that does not occur on its own. It requires an input, some form of external input. So this is what thermodynamics does. Thermodynamics talks about the direction of a reaction. So this is called an energy diagram. So when you want to extract iron from ore, you need external energy. When you want to cook food, you need external energy. The food will not cook on its own unless you add fire to it. So those are not spontaneous processes, but digestion is a spontaneous process. So moving on, what makes a process spontaneous? Again, we understand the fact that energy is conserved, but it does not tell about the preferred direction. So looking at some processes, when a ball rolls down a hill, what happens? It's going from a higher gravitational potential to a lower gravitational potential. So that means it's going from a place of higher energy or localized energy, so higher energy, to a more dispersed energy, because in the process it gives us energy. When the gas fills the container, like in this case, when the gas fills containers, it's going from an ordered arrangement to a less ordered arrangement. So there is a dispersal or spreading of matter. Since matter carries energy, so we can say that there's a dispersal of energy. Let me try to write clearer. So we're going from a place of order to, I don't want to call it disorder, but less order. Moving closer to dispersal of matter or energy. So heat flows from a cup, there's a hot cup of coffee that I drew at the back there. So the heat flows out to the surrounding. So there's energy in heat. So there's movement of energy, dispersal, spreading of energy. So the energy spreads outwards, increasing randomness. This is a chemical process, the iron going to rust. So that one is an exothermic energy from the exothermic point of view. So it releases energy, increasing the spread of energy. So we're increasing. So what we've been looking at, one thing that's common to all this is a disperser. So this was what I was trying to avoid writing very big here. When so same thing, when wood burns, it's exothermic. You're dispersing energy, but it's not always exothermic. For example, like we said, it depends on the temperature. When so at sufficient energy at the right temperature, water either freezes or it melts. At the right temperature or right experimental condition, your water freezes to ice or it melts. When the freezing releases energy and increases disorderliness, that is at that temperature. That freezing releases energy to the surroundings. Melting absorbs heat, increases disorderliness, and makes it spontaneous at other higher temperature. So what we have understood, at first, people thought that once it's exothermic, it is spontaneous. But what we have seen in the example so far is that even when you're going in the other direction, the endothermic direction, depending on your condition, you can still have a spontaneous process. So exothermicity, that is delta H, being negative, does not mean spontaneity. It's not a criteria for spontaneous reaction. So the criteria for spontaneous reaction that we have seen that is the randomness, disorderliness, or the one that I used a lot today, dispersal. So the spread of energy. So there must be another factor besides heat that helps in energy release or in dispersal that determines whether a process is spontaneous. So now with that, a new thermodynamic quantity is now defined. That thermodynamic quantity is called entropy. To understand entropy as we go along, so let's define again the concept of reversibility and irreversibility. So a process is said to be reversible if you're going from the initial process, you get to a final process. So this is initial state, you get to a final state, or whether intermediate state, and then you come back to that initial process. So a process is said to be reversed if you can restore both the system where you're interested in and the surrounding to the exact state. Then you say that process is reversible. So those usually happen when you move slowly or infinitesimally. So you have small changes. For example, in a class of like 500 people, you can easily, if people leave one by one, each step is a reversible process because you can easily bring one person back and everything is as is. But if like in a class of 500 students, like 100 people left at once, which is the normal thing, something going on, to bring them back, it's going to be difficult. So that would be an example of an irreversible process. In real life, processes are irreversible, meaning that we're saying that spontaneous processes are always irreversible. For you to reverse, it requires energy input. So, and that energy input is often different from the previous direction. Meaning, if this is the preferred direction, going back to A, so this is energy, delta H, let's call it delta H1. Going back in a reverse direction, the energy required, don't let me use delta H, so you require energy. The energy required energy in terms of heat or W required is often more. Okay. So what is entropy? We said that we have introduced another concept called entropy. Entropy is a measure of dispersal, amount of disorder or randomness in a system. So it indicates how energy is dispersed in a system during a process. Something coined by this guy sometime around the 19th century. Now we are in the 21st century. So it is related to various modes of motion in a molecule. Within a molecule, you have translational motion, you have rotational motion, you have vibrational motion, translational, vibrational. So the more you have all these motions going on, rotational. The more you have these motions going on, the more your entropy. So it is a state function. Remember why we defined our state function? So if you're going from a process 1 to 2, initial to final, the change in entropy is simply entropy of the previous one minus entropy of the final state minus entropy of the initial state. So also in a reversible process, especially during phase changes, that's when your temperature is often constant, the change in entropy can be calculated using Q reversible divided by T. So that would be the heat transferred during that process. One other thing, entropy is often defined using heat, not work, even though both are forms of energy. And why is that so? Heat often leads to, if you heat a system, it often leads to randomness. But if you apply work to a system, you are probably trying to create orderliness. So entropy is and heat are related that way. Spontaneous processes are driven by increase in entropy in the universe, and that's a statement of the second law. We'll soon get to that. Now, so we said that entropy is related to how the disorderliness of a system, and those disorderliness are related to different motions in the molecule. Each molecule, these motions that we are talking about, they are related to the different particles in the molecule. For example, water we know the structure of water to be this. So it has these different kinds of particles. So the position matters, the way they rotate amongst themselves matters, the way they vibrate among themselves matter. So in terms of something that we call microstates, I will describe that in a minute. Entropy is a function that increases the number of equivalent ways to arrange the components of a system. So like I said, there are different particles that are within a system, meaning that it is not just a macroscopic property, something that you look at. A macroscopic property are things that we see daily. Microscopic are things that we don't see. So the more ways to arrange a system, the more the entropy. So let me give there should be so now if you can see this picture right here. So inside this, so this thing reminds me of what we give babies to play with. But then we have put the 4 other particles inside them. You know, when a baby is crying, you shake it and the baby is happy looking at it. So there are 4 particles inside this, let's call this toy. There are 4 particles in there. It also has the shape of a dumbbell. If you put all the 4 particles in one of this place, there's only one way you can have it. Now, if you decide to put 3 particles on one side of the dumbbell and 1 particle on the another side, there are 4 particles. There are 4 different ways in which you can arrange them. Now, if you decide to put 2 in each, so they have been colored for us so that we know we can follow up how they are arranged. You know, if you have put them all in the same color. So if you decide to put them 2, you have it in 6 ways. So this reminds us of a combination and permutation. Now, entropy is related to how a system is arranged. If you are only arranging it in one way, then the entropy is low. If you are arranging it in several ways, then the entropy is high. Most likely, if you allow it to this system to be, it's probably going to move towards this where you have 6 possible arrangements. Now, each arrangement that we have here, 1, 2, this one, this one, this one, we call them microstates. So a microstate, formal definition now, is a specific arrangement or a configuration of particles in a system. Another way you can look at it, the number of classes that are possible, that's a specific arrangement. Each one at the molecular level has its own specific energy. So how is entropy related to the concept of the microstate state? According to, so the microstate is given the symbol W. According to this guy called Boltzmann, the entropy is equal to K natural logarithm of W. S is entropy, K is a constant. Again, remember, you are not allowed to memorize constants. Sorry, you are allowed to do what you want, but you are not mandated to memorize constants. Constants are usually provided. There's a book called The Table of Constants. And W is called the microstate. So for example, here, let me bring back the picture again. So here is one microstate that's possible for this. 1, 2, 3, 4. There are 4 possible microstates here. 1, 2, 3, 4, 5, 6. There are 6 possible microstates here, and so on and so forth. So the change in entropy for a process is then delta S final states minus the initial states. And if we use the loss of logarithm, it's W final, natural log of W final over the other one. So which means that if you're going from the state 1 to state 2, you're going to have K, the delta S will be, so here, I hope we are together. If we are going from state 1 has W equals to 1, state 2 has W equal to 4. So delta S for that process, delta S, that is going from state 2 to state 1 will simply be K ln 4 over 1. So we put in the value of K, we can calculate the delta S for that process. What we see is that the more, because this is the bigger one, so K ln 4 over 1, what's ln 4? I don't have that calculated. We know that this answer is greater than 0. So the equation shows that the entropy increases as number of microstates increases. So that's another property of increase of entropy. So entropy increases the more you have states to. Let me bring it to real world for us. Imagine if as a human being, you can only stay in a one-bedroom apartment. You're going to be localized in that place. That's it. But imagine now you're now given a whole floor that has like 5 rooms. You can now move around. Now imagine, now that's just one person. Now imagine that there are 3 of you that are staying in one room compared to when the 3 of you are staying in 3 different rooms. So you see, when you're in the one room, you are mindful of how you move around. But when you're in different rooms, you have more freedom. So you have increased entropy. So imagine those rooms, possibility of those rooms as microstep specific arrangements that you can have. So let's talk more. So that slide is not supposed to be there. At the molecular level, entropy, I've mentioned it, is related to the vibrational and rotational motions that are present in a molecule. Translational is a straight line motion. Vibrational, that is the vibration that occurs between bonds, the movement of the back and forth movement of bonds, or the opening and closing of angles. Then rotational, circular motion about a certain point. So the more those movements are present in a molecule, the more that a molecule has higher, the higher the entropy of that molecule. So entropy is associated with number of positions available to particles. Because of that, the entropy in solid state is much less than that in liquid state and is far less than that in that of gaseous state. In solid state, there's so much that you can move. One of the properties that we were told in about this classic states of matter, the classic states of matter are the solid, liquid, and gas. We have, I think, accepted about 5 states of matter, but I know that other states of matter have been proposed. So in gas, the molecules can move and they can occupy volume. So they have high translational motion, much more than in the liquid. So entropy increases with freedom of motion of molecules. And because of that, when you mix liquids or gases together, each particle has more available position, thereby increasing entropy. So this is the same thing that I just explained now. Light is not supposed to be there. But let me quickly say something there. So temperature increases entropy. Volume increases, you have more volume, that increases entropy. You have more number of particles, you increase entropy. Molecular complexity also increases entropy. Let's move on to the second law of thermodynamics. Okay. Can you hear me? Nobody has said anything. I hope so. Second law of thermodynamics is the one that tells us the preferred direction. It's the one that puts it into law, the preferred direction. According to the second law, thank you. According to the second law, spontaneous process, the entropy of the universe increases. So we are using the universe again. And remember, universe is system plus surrounding. So in another way, so that there's a line that I put here, the entropy of the universe increases for a spontaneous process. The entropy of the universe remains constant for the reversible process. So we're saying that regardless of the process, the entropy of the universe is either greater than or equal to 0. It is greater than 0 for an irreversible process, and that irreversible process or the spontaneous process is the natural flow of direction. So anything that goes naturally is the way of so that's a natural process tends to move towards states of disorder. So the second law provides criterion for spontaneity, dispersal of energy. Dispersal, so at times that when we just say it's dispersal of energy, we forget that matter also carries energy. So that's why often in other places you will see dispersal of matter and energy. Okay. So any process that decreases the entropy of the universe does not happen spontaneously. Please note that it's not that it doesn't happen. It requires energy for it to happen. It does not happen spontaneously. With the one that all of us use almost every day, the refrigerator, it's not a spontaneous process. That's why you need energy. So, recapping first law, energy of the universe is constant. Entropy is not conserved. Entropy changes for the universe. Now, the purpose of this slide is to show us the summary of what we just said. Energy of the universe, the entropy of the universe. The second law says the change in entropy of the universe is greater than or equal to 0. When it's positive, entropy of the universe increases. When it's negative, process is spontaneous in the opposite direction. When it is 0, the system is in equilibrium or you're undergoing a reversible process. Now, let's do some manipulations on entropy. When you do all these manipulations, you understand other concepts. So entropy changes in the surrounding. We can look at system, we can look at surrounding, but we're trying to lead somewhere. Remember, when your entropy of the system changes, it affects the system, it affects the surroundings as well. And it's not just, when we're talking about exothermic and endothermic processes, where we're focused on the system, because the total energy of the universe is conserved, and delta U or delta H for the universe is equal to 0. But here, we cannot focus only on the system. We need to focus on the surrounding as well. So there are two important things that we want to consider for that: the sign and the magnitude of the entropy of the surrounding. At constant temperature, we know that the delta H of the surrounding is equal to that. So how did we arrive at that? We defined delta S to be Q reversible over T. From our first set of previous lectures, we know that at constant pressure, the Q that you supply to the system is equal to the change in enthalpy. And because we are defining it with respect to system, then we have minus delta H. Recall the sign convention. When when the system does work, it's minus Q. So you have a minus delta H on the system. So what does this mean? If your reaction is exothermic, so that means delta H is less than 0 or it is negative. then delta S of the surrounding will be positive. Am I making sense? So from time to time, just let me know that you are still there. How many people are online? Okay. On the other hand, if it's an endothermic process, so endothermic, delta H is positive. If delta H is positive, then our delta S will be negative. So endothermic system usually does not favor spontaneity. Again, it doesn't mean that we don't have some endothermic processes that are spontaneous. It depends on the condition. Okay, so the magnitude, the other one that we said is the magnitude. The magnitude of the entropy depends on temperature at a constant T. And that makes sense because if you have a large denominator, then your answer or your quotient will be small. If you have a small denominator, then your quotient will be large. So delta H of the surrounding, the entropy of the surrounding depends on the delta H of the system and the temperature at which the process is taking place. So at high temperature, T is large, denominator is large. So delta S surrounding will be small. And if delta S surrounding will be small, delta S will of the system will be large because both of them are contributing to the delta S of the universe. So there's a tendency that the process will tend towards non-spontaneity at high temperature, but at low temperature, there's a tendency that the process will be spontaneous. And if you kind of look at it, what we're talking about now, you would see that freezing takes place at a lower temperature, even though that kind of looks like it's not a spontaneous reaction from the point of view of temperature. But when you look at the value of temperature now, from what we are talking about, you see that that at lower temperature, something drives spontaneity, which is the magnitude of the delta S of the surrounding. So spontaneity depends on delta S of the universe, which is that of the surrounding plus system. So we've looked at delta S entropy. Now, so, a function of the system, a function of dispersal of energy. It's not only a function of what you are looking at. You know, most of the times you consider the system, that's what you're working on. You don't consider the surrounding. Something came to my mind also. If you consider a human being and that wants to just say that, okay, I don't care about other person, it is only about me. The natural order of things will take place if you're not too careful. The people that surround you can affect the total. You can also zoom in. Okay. Okay. Okay, so there's a suggestion for some people here. Please, if the video is not clear on your side, please try to zoom in. The video is clear. I'm looking at it on YouTube so that I know what you're looking at. Okay. If we put what we have set together now, for any process, this is not from second law, please. For any process, delta S of the universe is equal to delta S of the system plus that of the surrounding. And we know that for the universe, delta S is greater than or equal to 0. So that's, by the way, equal to 0 is equilibrium, greater than 0 is spontaneous. We know that at constant temperature and pressure, delta S of the surrounding is minus delta H of the system divided by T. That's what we said in the previous slide just now. Actually, okay. If we substitute this into the equation of the universe, that is, put delta S for surrounding here, we get this expression. Now, rearranging or doing some mathematical manipulations, we get this expression. A very important expression in the field of thermodynamics. This quantity, minus T delta S of the universe, abbreviated here, so univ and universe stands for the same thing. It's called the change in Gibbs free energy of the process during that process. And what is the Gibbs free energy? Gibbs free energy is defined as enthalpy minus temperature and entropy multiplied by entropy. Defined in words as the available energy available to do useful work at constant temperature and pressure. We won't go into too much mathematics of it, but G, or change in G, is also another useful quantity to quantify whether a process will be spontaneous or not spontaneous. So if G is defined as H minus Ts, then change in G during a process will be changing G in H minus T delta S. So it's not, delta T is equal to 0 because we are working at constant temperature. So there's no minus S delta T from the point of view of mathematics. So if we now relate this, that delta G is the minus T times delta S. So now if you look at it, H is a function of the system. Delta G is a function of the whole universe. Okay. Delta G is proportional. If you look at it, delta G is it's T minus T times change in entropy of the universe. It is proportional to the negative energy of minus delta S universe. Negative of minus delta S universe. We have said that for a spontaneous process, let's expand that. We have said that for a spontaneous process, delta S of the universe must be greater than 0. If it's going to be greater than 0, then we can use our delta G in this case. When delta G is less than 0, the process is spontaneous. So that's one condition that you have learned in your in the ordinary chemistry teaching. So this is where we get delta G less than 0 means that your process is spontaneous. If delta G is greater than 0, delta U universe is less than 0, then we are looking at a non-spontaneous process. Delta G equals 0 means that we are looking at a process in equilibrium. Okay, let's move on to the third law. Okay, so this is not supposed to be here. The third law. No questions so far. One thing is that once you keep lowering temperature, most things try to stay in one place. We see that a lot in our animals. And the animals that hibernate during winter, they just go and stay deadly in one place. So as you lower temperature, motion reduces. That's where I'm going. So the different kinds of motion, translational motion, vibrational, rotational, all of them reduce temperature. So once you reduce temperature, you have fewer accessible states to stay. And if you have fewer accessible states, then you have lower entropy. According to this is not Boltzmann this time around, I've forgotten the guy. The third law, according to this third law, the guy that came up with the third law, when you're able to get to absolute zero, I don't know whether I was in this class that I mentioned it, but the concept of temperature born out of the concept of heat and work done. So when you're able to, if you're able to approach absolute zero, the entropy of a system is equal to zero. Of a pure perfect crystalline is equal to zero. S of K, S at K is equal to zero. What does that mean? A perfect crystal has no defects. That it's perfectly perfect. Anyway, a perfect crystal is not useful in what we are in many engineering terms today. But then we are not working at absolute zero, so that's fine. What's the time? 9:54. Oh, I can definitely not finish this today. And mostly what I have left is the worked example. At 0 Kelvin, a perfect crystal. So let's look at it. If you're able to get to that absolute zero, the number of microstates that you have will be equal to 1. If it's equal to 1, from Boltzmann equation, S is equal to 0. So what this does, that at the third law, what it does in the long run is that it provides an absolute reference point for all entropy measurements. So any entropy that is given, so if you can say that the entropy of a system, not change in entropy, but if you can say that the entropy of a system of hydrogen gas is 130 joules per mole per Kelvin, it means that you're saying the entropy that at this temperature, it means that you're saying that the entropy from absolute zero to the state you are, that is 130.7 joules. So entropy changes with temperature. So as temperature increases, atoms begins to translate, molecules begin to vibrate and rotate, and microstate increases and entropy gradually increases. Long and short, entropy has a true 0 point. So what I mean by 0 points is that it has a reference point from which you measure it. Unlike enthalpy, if you remember, absolute values of enthalpy cannot be measured. A reference relative value was assigned. That reference value will say that the enthalpy of formation of elements in their standard state is equal to 0. So those are different. So there are standard entropy that have been calculated, that have been determined over time for different substances, gases, and so that molar entropy is defined as the entropy of 1 mole of a substance in its standard state. That standard state is often at around that 298 Kelvin, which is mostly the room temperature in which human beings work. I think it's the optimum temperature that people perform experiments. So standard state, again, it's a pure substance at pressure of 1 bar and at about 298 K. Now, usually the pressure is always set to be 1 bar. The temperature can change from time to time. Entropy is an extensive property. It depends on, it's a function of the amount of substance present. So this is where I want to go here. If you remember, delta H of formation of H2 is 0. So H2 gas in its standard state. So all these are in a standard state now. gas, liquid, solid at temperature, I think, yes, this is about 298 Kelvin. So you don't have anything zero. The only time that you have entropy to be zero is when you are at, please, could you send the notes after class? So if you were here, what does this mean? The lane in the equation S equals K. Damilola, your question is S equals K ln W. You are asking what Ln means. That's natural log. Ln, natural log. If you are late, you can't ask question. There's a question here. Do we have to memorize? Can somebody help me answer this question, please? Do we have to memorize all these values? This table that I'm showing, do you have to memorize it? Thank you. Why would you memorize it? Good morning, ma. Can we come over to sign our chemistry manual today? You see, this is the kind of question that make people annoyed. And then you say that lecturers are. Thank you. Thank you for those that have answered. So the other question here, the key difference between enthalpy is heat content. Entropy is disorder, amount of disorder in the system. Don't let's go into too much physical chemistry. Ln is not a constant. Okeke Ikechukwu. Ln is natural log. How would I say it now? The same thing as, you can write log something. K is a constant. Ln is not a constant. It's when you're talking about indices and logarithm. Okay, any other question? Okay. Clausius and Kelvin statement of second law. And you can go and read it up. It's not in what I have given. Energy stored. No, they are not the same thing. Energy stored is stored in chemical bonds, blah, 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 and all that. So that energy stored is mostly related to that's the lane on the calculator. Let me say something on these values before we close for the day. Yes, you will see lean on calculator. So let me quickly say this. So this is the table that you were looking to memorize before. But this table, there's something that we observe from the table. Number one, elements in their standard states are not equal to 0. For elements in their standard states, S is not equal to 0. More like it. S is not equal to 0. It's not a constant. It's like ln x in further math, meaning 1 over x. Ibo nìyẹn tún ti wá báyìí. Ln x is not 1 over x. Sorry. So gases have higher entropy than liquids. So let's see. Gases, liquids, lower entropy, solid. Okay. Okay. Gases have, and that makes sense because when you are melting a substance, if you follow this line, when you're melting the substance, heat is absorbed and it's at constant temperature. Molecules gain freedom, motion, and when they gain freedom, entropy increases. Entropy increases with molar mass. Heavier molecules can store more energy. And when you can store more energy, it means you have more microstates that you are working with. Entropy increases with number of atoms. And you can look at this from the point of view that when you are going from atom to molecule, atoms, a single atom can only translate. It cannot rotate with itself or vibrate with itself. When you're talking of vibration, you're looking at two or more particles. So, and then when you have more atoms in a molecule, then you have more reasons for molecular vibration and rotation. So molecules, entropy increases with number of atoms in the molecule. Entropy also increases with dissolution. So, and then there was one other thing that I said before. When you increase the volume, entropy increases as well. We will stop here for today. We will round up our class on Monday. Any other question? Unless you tell me to continue, and I will continue because I really wanted to finish today. I don't think. And somebody does not like my voice. Okay. Continue. For substances that sublime, I did not see this one before. So there's a question here. For substances that sublime, so we are looking at it at a constant temperature now, other things equal, would their entropy increase? Okay, I'm not teaching anymore. I'm just, for the next 10 minutes, I'll just answer some questions. So for those of you that have other classes, you can go for your classes. I'll continue teaching on Monday. So there's a question here that if a substance sublimes, does it, during that process, is there an increase in entropy or a decrease in entropy? And then there's another question on YouTube. So if it sublimes, the entropy increases. Yes, it will increase. It increases. It increases because you are increasing molecular motion. The concept of microstates. Microstate is, how did I explain it the other time? Available space. So think of it as the available space to for a particle to be in. So if you have more available space to move around with, then you have more microstates. And if you have more microstates, then entropy will increase. Yes, thank you, Olaleko Emmanuel. Entropy increases. Any other question? Somebody said I have a question and did not ask the question. And even two persons, I have a question and they did not ask the question. How am I supposed to know it? Moshood, my office is at the main faculty of science, room 147. Let me see. The sites, the place where you got my previous notes, this entropy note has already been put input there. So let me share that again. Is there an upcoming test? The test will be announced by the coordinator of the course. How did they get this entropy standard of formation? If I understand the question, you're saying, where did those values come from? That's a Ashiru Munirat from YouTube. If I understand the question, the way I understand it is, where did they get it? So there are so many experimental measurements that have taken place over the course of 70, 100 years. And there are different methods. There are three main methods in which you can use to determine entropy. Okay, so one more minute. Any other question? Okay. I've answered the question. Okay, Irene, I don't understand your question. Since microstates contribute to level of entropy, do we also consider microstates? Can you rephrase that question, please? Or macrostates. So macrostate is going where? Is it in the first one or in the second one? So whichever way, sha. So how would I explain it? So macrostates, let me come back. Only second one. Which one is the second one? Got it. You can't rewrite the whole thing again. So when you're talking about macrostates, you're talking about those things that you see, that you measure. So you take thermometer, you put it in a sample, you measure it. So you are measuring the resulting macrostates. So that macrostate that you're looking about is an ensemble or a collection of several microstates. So the several arrangements of any form of microstates that you can look at. Let me give you an example of a microstate. In a school that has 12 arms of people in GSS1, me that I'm coming, I only know that there are 12 arms. Now, how are the children arranged? Now, you can now link that one to microstates. The only thing that I know is that there are 1,200 students in GSS2. How they are arranged, that's when you're talking about the microstates. So the macrostates, let me write it. The macroscopic observation macrostates. That's where you measure your entropy, your temperature, your volume, and so on. The micro is the one that leads to them. In gas, do properties aside temperature, like density, affect entropy values? Yes. Pressure also affects it as well. If you make, how would let's look at it. When you're looking at density, for example, density is mass over volume. So when you want to change the density, you are probably going to change the volume. And when you change the volume, you will change the entropy. Okay, I'm done. Oh, I've tried. Why is Moshood looking for me? Room 147. Yeah, this àwọn ọmọlábí ìwé la rí gbogbo wọ̀nyí yìí. When you are saying that the microstate refers to the number of arrangements in the particles, the macrostate refers to the number of particles. That is one way. It's a collection of several macrostates. So that is one way that you can do it. So Babalola gets it. I don't know. What was that question? You are free to come and ask questions in my office. You see. So how did you get the first slide? How did you, the way you got the first slide is the way you are getting the second slide. Okay, so after this last question from YouTube, it's the people on YouTube that are fitting, because I know that there's a delay before they get it. So Bolaji Saka said, subliming substances, do they have more entropy than normal substances? Now, the sublimation in itself is a process. It is not about the substance. So the entropy of the substance, depends on what is in that substance at that process. The fact that it can sublime is now something different. It has nothing to do with whether entropy or not entropy. It's just the nature of the system. Then sublimation again depends on the condition. Some substances may have the tendency to sublime at low temperatures than others. So I hope I'm able to answer your question, Sha. So general overview of things. Adeni Lola said that you just gained admission. So anytime you just get somewhere, you need to ask those people that are there first, just like some other people ahead of you. So please, your class reps have access to it. So class reps, please share the link again. Okay, see you all on Monday. I said that I have uploaded the slide to the site again over and over and over again. Ẹ fẹ́ pa kẹ́tẹ́kẹ́tẹ́ ni.